Okay, this is section 4.1, but it's the beginning of the chapter, and the chapter title page is on page 154. You see the title of the chapter is called Polynomial Functions. What we studied the last chapter, in case you weren't aware of that, by the way the test was just quadratics. This goes a step further, and now we're going to have other powers on x besides 2.
I just found my other half of the view. Should I figure that in or not?
I suppose. Get up there and put it right there on that stack.
Thank you.
A polynomial, well, we're about to find out what a polynomial is. You can't study polynomials if you can't recognize them when you see them. That's one of the first things we're going to learn in section 4.1. The title of 4.1 is Graphing Polynomial Functions, and most of your graphing is going to take place in your calculator, and then I'm going to teach you to carefully copy it on a written document. Very carefully. If you're going to have the calculator do all the grunt work for you, you got to be really good at copying it since you don't have to plot points. So I'll show you how to do that in a minute, but we got to first learn to recognize a polynomial when we see it. So if you will get your eyes with me on page 158, that's where things begin. I'm going to do a little exercise with you called concept development. You learn about it in your classes when you learn how to go to these education classes, learn how to teach people. It's one way to learn something, and it's pretty appropriate for this. In concept development, just to show you what it's like, you do concept development in your mind without even trying, most of the time. Like, for example, when you were really little and just barely able to talk or make little animal sounds or whatever, even at that point, you were able to tell the difference, for example, the difference between a dog and a cat, even if they were about the same size. Your mom would say, what is that? And you'd say something to indicate it was a dog. You'd probably bark or something, and then the cat would wander by and you would know the difference. And yet, in a lot of cases, they are virtually the same size. They have fur all over their bodies. They have 4 legs. They have a tail. They have ears at the top of their head. There's just a lot of things about them that are alike. They have whiskers. It's very clear that they are different animals, and you knew even at that age the difference between the two because you had seen several examples of dogs and several examples of cats, and your mind, without effort, made the distinction for you. You didn't have to be taught the difference. There are differences. They're subtle. Cats tend to have smaller, pointier ears. Cats tend to have a lousier attitude. I hate cats. They won't come when you call. My grandpa always said, I don't have any use for kids or animals that won't come when you call. I feel the same. Dogs are generally more playful. Cats generally don't have much to do with you. Some of them do, if you're going to be nice to them and they can get something out of it. I hate them. All right. There's a joke that I saw. You've probably heard it, but the dog will look up at you and say, and think in its mind, it'll say, oh, they feed me, they keep me warm, they love me, they must be gods. You heard this? The cats, they look up at you and they say, they feed me, they keep me warm, they love me, I must be a god. That's the difference in attitude. Okay. All right. So what we're going to do is this concept development from the ground up with these things up here. All of these things up here are expressions that start with y equals. So that's something they have in common, like having fur all over the two animals. And but there are some differences. So what I'm going to do, much like your parents would do, is they would say, no, not all at once. They say, this group over here, these are cats. This group over here, these are dogs. And your mind will also automatically determine whether they're good or not. Some of these up here are polynomials and some are not. So I'm going to put a check mark by the ones that are polynomials. And I want you to study those that are against those that are not and see if you can tell a polynomial when you see it. This one is a polynomial. So is this one. That one's not. That one's not. That one's not. This one is not. This one is. This one is not, this one is, yep. This one is not, and this one is. So the red ones are polynomials. The black ones, the ones that don't have a check mark, they are not polynomials. So study those for a second. See if you can make some distinctions. Okay, can anyone tell me why they believe, for example, why they think this one is not? And it is not. Why do you think this one is not?
Is it because of the negatives?
Negative what?
Negative exponents.
So you may think that that's what it is. So you look around for all of the ones that are and see if any of them have negative exponents. They do not. So that's probably a good distinction attribute. You can't have negative exponents. That's true. You can't. That's a good observation. Why do you suppose this one is not?
It's not simplified all the way.
Simplified doesn't really matter. Even if you hadn't collected like terms, it may still be a polynomial. So it's not the simplification, but that's a good thing to notice. And I don't think you could simplify that further. Fractions. You look around. Oh, this one's got fractions.
No. It has a third variable.
What?
It has a third variable. Has a z. Or is that, no, unless it's yes.
This is a y over here, and all of these, if there's a variable over here, they're all x's.
If that's that 2, it's a z.
Oh, no, it's a 2. My z's are crossed because my 2's and z's look so much alike. That's a 2 on the end. Let me tell you.
Is it
This, what?
Oh, sorry.
Go ahead.
Oh, is it because the x is the denominator? That's where the denominator.
Yes, and that leads to the very same reason why this is not. Because if you will think about it for a second, if you remember exponents, negative 3 over x squared is the same as negative 3 x to the negative 2. Because when you bring it up, it changes the sign on the exponent. So now we're in this boat, see? It wasn't very clear because the exponents appear to be positive. Like this one still appears to have an exponent of 1. It does not. If you make it so there's no fractions, it is a negative exponent, just like these had. But you have to remember some rules for exponents. So these two are not for the same reason, but this one wasn't as clear. Okay? Why do you suppose this one is not? What makes this different from the others? The ones that are. There's no negative exponents, so it's not that this time. Yeah, well, mainly, yes, and you're right. If it was just a y term, I could join it with this one over here. Just toss it over. But this term has got 2 variables in it, 2 different variables. So does this one. This one doesn't, but these two, if there was even just one that had a y in it as a piece of the term, part of the, as a product, cannot be a polynomial. Polynomials can only be written in one variable. This has 2. I could just as easily have put a z here and a z here or whatever. You cannot have 2 different variables in the same term. Now you're out of the polynomial realm, so that one's out. Why is this one not? Yeah, for the same reason this one and this one are not, if you think about it. This can be rewritten as x to the negative 3, which automatically takes it out of the running. And this, 4x to the negative 1. It doesn't matter that this satisfies it. All terms have to satisfy the positive exponent rule. Why is this one not? What's that?
No, it's not.
Then I need to put another one up here if that's what you're going to say, because I didn't put that up there. I need to put 2 more up here that are polynomials. This is a polynomial. I can even put a +4 on it. And this is also a polynomial. So what what you said, because I didn't have a really good example for you to distinguish it from, what you said is there's no exponent on this. There actually is an exponent on this. This is another thing that you have forgotten. What?
Oh, it's not. I was thinking that it's because of the x being cubed, square rooted.
It is square rooted. And does anybody remember, I know you've learned this, it's been a long time though. Does anybody remember the exponent that can replace that square root? 1/2. If I added something else to this, like this, 4 times the cube root of x squared, you can replace this with x to the 2/3. Either one or both of these keeps it from being a polynomial. Are you starting to get some idea what makes a polynomial? This one fails because its exponents are fractions, not whole. This one is a polynomial. Some people say, well, because that's a square root, it can't be. No, the number or the coefficient, remember, you guys all know what a coefficient is? Do you know what a coefficient is? Shake your head if you don't. Coefficients can be anything that's real. Anything that's real. Can't be imaginary. We're not going there. Anything that's real can be a coefficient. Even irrational things like pi and square root of 2 and square root of 2. These are both polynomials. It's the exponents that make it, not the coefficient. The coefficient can be virtually anything as long as it's real. Fractions or, like, see, here's one, fractions. Let me put one more up here that's a polynomial. I want to show you this because it's kind of a subtle thing. I'm going to put 2x over 5 plus 3 x to the 8th over 4 plus 2. This is also a polynomial. It's all about the exponents. See how they're whole in the numerator? Not just whole. Well, yeah, I'll talk to you about that in a minute. But they're in the numerator, they are positive and whole. The rest of this doesn't matter because really, truly, if you think about this, that thing right there, this expression is the same thing as this. You buy that? You okay with that? This is the same thing as this. So that makes it a polynomial because it's these that seem to be the delineators. And sometimes it's hidden, as it was here. We put the x squared down below, but it's really, if you put it back up here, it actually gains a negative exponent, which keeps it from being a polynomial. But the numbers in front can be anything real. Fractions, irrationals, whole numbers, negative numbers. Where's a negative number? I'll do it right here. There's a negative number. Still a polynomial. Still not a polynomial. This is a polynomial. There we go. Even this is a polynomial. Now, this is subtle. This is tricky, and this is where I want to have the discussion about what exponents actually are, the exponents that belong. This is really 5, or y equals 5x to the 0. We never bother to write that, because as you remember about exponents, anything to the 0 is 1. So this is 5 times 1. So we don't bother to write x to the 0. But if we wanted to know why this is a polynomial, it's because it has an x, it's understood, an x with a whole numbered exponent. Do you remember what the whole numbers are? Natural numbers are the numbers you count with, like 1, 2, 3, 4, 5. Whole numbers are only one element bigger. 0, 1, 2, 3, 4, 5. No fractions, no negatives, no irrationals. 0, 1, 2, 3, 4, 5. As long as exponents are members of the whole number set, that, and that, and that, and that, and not that. That's not a whole number. So that's out. This isn't a whole number. Those are not whole numbers. It's not a polynomial. Exponents have to be whole. You everybody got it? Okay, so there's certain names for certain types. Let me tell you about this is vocabulary. This is all lingo we're going to be using for the rest of the chapter that you got to get used to. This is a polynomial, and it's a polynomial of degree 2. This is a polynomial of degree 4. This is a polynomial of degree 4. This is a polynomial of degree 6. This is a polynomial of degree 5. This is a polynomial of degree 1, degree 0, degree 8. Do you understand where I'm getting those from?
Everyone except that bottom one on the middle.
Right here?
Yeah.
It's of degree 5 because of all the terms, the highest power that occurs determines the degree of the entire polynomial if they're out of order. The highest power determines the degree. Okay? So this is a degree 0 polynomial. See that? This is a degree 1. It's understood right there. See it? Okay? A lot of these had the highest power in the front. Like this is what we expect. This one. This one didn't. This is a degree 2 because of this 2, not this one. This one. They're out of order. But this one was in order. This is a degree 4. But you're looking through, scanning through all the terms, and wherever the highest power occurs, that's the polynomial's degree. By the way, these things I'm about to circle are called the leading term. Whether they lead or not is irrelevant. It's what's the power that determines it. This is the leading term along with its sign in that one. This is the leading term. There's no more polynomials. This one right here is the leading term. Leading term. Yep. Leading term. Right there. Okay. Leading term is here on this one. Here on this one, including its sign. And here. Now, these things that I'm about to circle are what we call the leading coefficients. It's pretty obvious. You find your leading term, and it's the coefficient on that term. This is the leading coefficient. That's the leading coefficient. Negative 2/3 here. Pi here is the leading coefficient. Negative 7 here. 3. That's the leading coefficient there too. I failed to circle that one. I should have in blue. Here, the leading coefficient on that one. Okay, so we have a leading term, we have a leading coefficient, and the coefficient takes on the sign of the term. Leading term, leading coefficient. The degree of the leading term is the degree of the entire polynomial. And the leading term doesn't always lead. It's just the biggest one, biggest power one. So, now, would you take a look with me at the table on page 158? Just above example 1, it talks about 4 different degree types, and they have certain names. You have to get used to the names; they're not hard. If you have a polynomial of degree 0, like this one, erase that. It's a constant function, duh. Because the y is always 5, it constantly has the same value, and it's a horizontal line if you graph it. Yeah, constant. We call that a constant function. If you have an x in it that has just a single power that's understood, like this one, this is a line. Y equals mx plus b. It's a slanted line. This determines the slope. This determines where it hits the y-axis. We call that linear. Root word is line. If it's a second degree polynomial, we call it quadratic. We spent the whole last chapter studying that. If the leading term is of 3, is a degree 3 term, we call it a cubic function because cubes have 3 dimensions, length, width, and height. We call it a cubic. 3 is the leading term, the power leading term. And if you have a 4th degree polynomial, we call it a quartic. You can get crazy and go on up from there having to do with the Greek, but we are not going to. For example, we will just call this an 8th degree polynomial or a polynomial of degree 8. It's really called an octanomial. Dumb name. You very, very seldom see anything greater than quartic. As a matter of fact, your calculator only fits up to quartic curves. It doesn't fit anything higher than that. We'll talk about that a little bit later as the chapter rolls along. Would you look at example 1 with me on page 158? Do you believe that the thing you're looking at in the A part of example 1 is a polynomial? Is it? You're pretty confident?
Yeah.
Okay. What is its degree? What is its leading coefficient? What type of polynomial is it? Cubic. It's a cubic polynomial. It's actually called a cubic trinomial because there are 3 terms. Okay, but that's a cubic polynomial. And I think I asked you everything else. Is B, look at B, is that a polynomial? Okay, so since it is a polynomial, we have to answer some other questions. What is its leading term? What is its leading term? Square root of 2x to the fourth. Root 2 is just its leading coefficient. I ask you for the leading term, so you have to name the entire term. It would be root 2x to the fourth. You agree? Term, coefficient, they're different. What's the degree of this polynomial? What type is it? Quartic. Okay? Leading coefficient's root 2, we discussed that. Look at the C part. Is that a polynomial? Where does it fail? An exponent, actually. An exponent of -1 on one term eliminates it. So because it's not, we don't have to answer any questions about it. Is D a polynomial? I didn't discuss that one very well, but I had one like that right here. This is not a polynomial. This one's not a polynomial because its exponent is not real. I mean, not whole, for sure. We don't know anything about it. This is not a polynomial. Exponents must be whole. Exponents on anything must be whole. In other words, the variable cannot be part of the exponent and still be a polynomial. That's called a power function. No, it's called an exponential function. Okay. Anyway, so that's the reason why D fails, because we have a 3 to the x term. Okay, take a look at example 2. Example 2 says to evaluate. What does that word mean to do in math? More informal terms. What does it mean to do to evaluate something? It's a phrase, 3 words, 1 syllable each.
Right, so you look at it.
No. Looking at it does not evaluate it.
That was pretty good though.
Plug it in. Plug what in this case? No, look.
Free. Oh, free.
Plug in 3. It says at the very end, evaluate this polynomial when x is 3. So, you plug in 3. But let me show you something. We're going to make the calculator do the work. But in order to get full credit for something like this on a test, you must show what you're asking the calculator to do. You have to show it with writing, with pencil, on a paper, and then you can make the calculator do it. But you have to show me what you're asking it to do. Not just imagine it, show it. So, if what you see in this book is what's written up there, which is 2x to the fourth minus 8x squared plus 5x minus 7 when x equals 3. So this is what your eyes are looking at in the book. You are going to write this on your paper, and especially on your test paper for full credit. You're going to write 2 parentheses, 3, 4, up there, minus 8 parentheses, 3 squared plus 5 parentheses, 3 minus 7. And then you can grab your calculator. Because if you screw it up by typing it wrong in your calculator, I can at least see that you knew what you wanted the thing to accomplish. Does everybody know how to raise something to the fourth? You all know how to raise something to the fourth in your calculator? It's right here. And I know most of you can't see it very well, probably. Let me pull this back. This is your raise to key right here. They call it a caret. Got a little hat. For those of you watching this video, it's right here. This is the raise to key right there. Right underneath the clear key. So, the syntax, just so you understand, the syntax means how you type this thing in here. This is the actual things you would type. You would write 2, and then a parenthesis, and then a 3, close it, and then a little hat. That's your caret key. And a 4. It'll type it big like that. That means 3 to the fourth. It won't take 2 to the fourth as well, just the 3. Minus 8, parenthesis, 3. And you already know where to get that. You've been using that all last chapter. So you just hit the square button. Or you can hit this and a 2. And then plus 5, 3, minus 7. So that's what you're going to type into your calculator. 2, parenthesis, 3, close it, raised to the 4th. Minus 8, 3, squared, plus 5, parenthesis 3, close it, minus 7. What are you getting?
98.
98. What you found here, folks, believe it or not, is this polynomial, which was written f of x, this is f of 3. That's what you're really doing if you want to know the notation. And what it says is, when the x value is 3 on this grid, by the way, there are billions and billions of points on this polynomial. The thing curves around all over the place. But if you go out to 3 on the x-axis, you will have to go clear up to 98 to hit it. That'll be the y value that goes with 3. That's what you just found out. Did you see this? In other words, folks, this expression right here, f of 3 equals 98, is just like saying this. This is a point on the parabola, or on the polynomial. This is a point on it. This is another way of writing a point. So when x is 3, y is 98. That's what it's saying. Get used to it. So we just evaluated this thing when x was 3. Plugging it in. How would this look different if it had been written like this, but it said when x is negative 3? How would that change? Inside the parentheses. The negative on that 3 belongs inside because you have to power not only the 3, but the negative sign. It's all got to be powered. So every time you open a parenthesis, you put inside it exactly what it is you're substituting. That's what you would put in your calculator too. Here, here, and here. I don't know what that is. Try it out and see. What do we get for that one?
68.
68. Okay, so that means that what we've discovered here is that f of negative 3 equals 68. What that means is on the graph of this polynomial, if you went back 3, you'd have to go up to 68 to get it. Whereas a positive 3, you'd have to go up to 98, so it's not symmetric. You following? Okay, moving on. Next thing I want to discuss with you is what we call end behavior. End behavior of these polynomials. Polynomials, by the way, folks, polynomials tend to wind around on the graph. They go up and they go down, they go down, they go up, and then they finally end up to the left and to the right. They finally end up taking off somewhere and they never come back. You'll see that as we go through the chapter. You'll start to be able to analyze those kinds of things. But I want to show you how you talk about and write with correct notation a thing called end behavior. Okay? If you have a function like this is just an example. But if your function looks something like this, and you put it in order so it's in standard form, and you have, like, for example, 4x to the 6th plus, and I really don't care about the rest. It's all about that leading term. That's what we're about to do. Okay? So it's 4x to the 6th plus blah, blah, blah. If this is the biggest one, or your leading term, and you put it in the front where it belongs, these are the things you have to observe. Shh. The leading coefficient is what? 4. And what you have to observe is not just that it's 4, but the main thing you have to observe to do this little thing I'm about to show you is that it is positive. Leading coefficient, the number on front, is positive. And along with that, you have to observe whether the exponent, not as positive or negative, it always has to be positive, but we're not talking about a polynomial, right? So this isn't positive or negative, it's odd or even. Sorry, the degree of the polynomial, which is the degree of the highest term, which we assume is on the front right here after we put it in order. And the degree is even. If both of those are true, leading coefficient is positive, the degree is even, then your graph's end behavior means when x gets really big to the right or gets really small to the left, what ultimately happens? This is what ultimately happens. Remember, this is just an example, but all of these will have this end behavior. If this is positive and this is even, by the time they finally take off and never come back, they will always take off up. What happens in between is not what we're interested in this discussion right now. This could wind around and do different things. But eventually, that's why it's dotted, because we don't care about that part. But eventually, the end behavior on this is going to end up going up here and up here. It's the notation that kills people on this. It's how we write it, so pay attention. When you see this expression right here, what does it mean to you? This f of x, what does that mean? It's the y values, or the vertical values on a graph, right? F of x is the y values. This is the x values, and they are horizontal. X is all about right and left. Y's are all about up and down. Yeah? So this is what you write. For this idea right here, you say f of x, meaning the y values, go to infinity. That means up, because it's positive. It goes up forever. As x goes to the right. If I let x get huge, y's are getting huge also, because this thing's headed up. To describe this one, we say f of x, which means the y values, go up. They're headed up to infinity as well, as x goes to negative infinity, because I'm saying what happens? I'm going way, 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 way left on the x-axis, way big, huge, monstrously huge negative numbers. What are the y's doing as I do that? Going up. The fact that both of these infinities are positive on the y values means it's going up. We're going right, and it goes up. We're going left, and it goes up. And I know you're going, how come that's pointed to the right? It's saying as x goes to negative infinity, means actually moving this way, the y's are going up. You follow me? Which we express it with infinities. Okay, here's another situation. It's also just an example. If I have f of x like this equals negative 2/3 x to the 4th plus, I don't care what follows it. Well, it's all about the leading term if you put it in order. So this time, the leading coefficient is negative. And the degree of the polynomial is still even. What happens? Branches go down. So, in this case, at the end, where it's never going to come back again, it's going to be going down this way, and it's going to be going down this way. What happens in between? We don't care. It's about end behavior. In this discussion, we don't care what's good, all the curvy stuff that's going on in the middle. We care what happens ultimately. So how would you describe this with that kind of notation? You start out with f of x. What does it do? It goes where? Negative infinity as x does what? Goes to infinity, because we're going right. What's happening? We're going down. See? How do we describe this one? What's f of x doing? Yep, going down as x goes to negative infinity. As it goes left, it's going down. Both of the y values are headed down as x does either one of its things. That's what we're saying there. You follow that? You see, understand the notation? Okay. Move over here. Don't get dizzy, whoever's watching this. Okay, so we've considered when the leading coefficient was positive, and the degree was even, negative, degree is even. What do you suppose we should consider next?
Well, just go straight. One goes up and one goes down. We already discussed that.
Constant ones are just big. What's that?
One goes up and one goes down.
Okay, well, that may be what happens, but look at the line where it says leading coefficient negative, degree is even. We've looked at both situations where the degree is even. We should let the degree be odd, and we should start out with a leading coefficient that is positive, usually. Just to investigate all the possibilities. So if I say f of x as an example equals the square root of 2 x to the 7th plus blah, blah, blah. Don't care about the rest. It has no effect on end behavior. Then this when I look at that leading term, I can see that the leading coefficient is, what are we looking for? Odd or even, positive, negative, rational, irrational, what are we looking for? Positive or negative. Leading coefficient is positive. And the degree is odd. It's going to be odd or even. So we've got that situation, and I'm here to tell you this is what's going to happen. It's going to go low over here and end up high out here. What happens in the middle?
We don't care.
We don't care. That's pretty crappy. Turn sharp there. Now it's headed up. Okay. So this is what's going to happen. It's going to. This is the quick reference that I have for you. I mean, without using all that formal language and goes to infinity and negative infinity and all that stuff. I say if the leading coefficient is positive and the degree is odd, it starts low and ends high. Over here, I would say if the leading coefficient is negative and the degree is even, it starts low and ends low. Just to get the idea out quickly, but that's very informal. Okay? So this thing starts low and ends high. How do you describe this side of it? Starts out f of x goes down, yeah, because that's a description of up, down, as x goes to negative infinity. It's going left. So how do I describe this one?
X goes to infinity also.
Okay, so in this situation, both the y and the x are doing the same thing. Right and up, left, down. Starts low, ends high. Okay with that? And the last thing to consider is what kind of a leading coefficient do I need? A negative one. And what kind of an exponent do I need on x? What's that? That's weird, but I mean, nobody gets as high as 11, but we're going to go with that. Other stuff that follows it, doesn't matter, have whatever follows it, it could be just that. And this will be its end behavior. It will start high and end low. What happens in between is something we don't care about. How do you describe this behavior?
F of x goes to positive.
Yep, that's up.
And x goes to negative infinity.
Yeah, it's on the left side. This one over here is going to be?
F of x goes to negative infinity.
Yep, down.
X equals goes to positive.
X goes right. Notice that the signs are opposite when this happens. So it's pretty easy to remember. If the degree is even, both of the end arrows are going to go one direction or another. It's pretty easy to remember which one's which. If it's positive, it goes up. The leading coefficient. If the leading coefficient is negative, they go down. That one's not too hard to remember. This one could be a little rough because it's hard to, you say, oh, it's odd. That means it's going to go, they're going to end up in opposite directions, but which one's which? This is negative, negative. This is positive, positive. I don't know if that helps you at all, but you're going to have to memorize which one's which. Low then high is the positive leading coefficient. High then low is the negative one. These have the same sign when it's even. When it's positive. They have opposite signs in the description when it's odd. I didn't write that down. Leading coefficient is negative, and the degree is odd. Okay? You're going to have to be able to look at any polynomial, find its leading term, and decide what the end behavior will be. Okay? So take a look at the next example based on what we just had a discussion about. And let's see if we can describe what's going on without, well, they actually show you a graph, which is unfortunate. But let's see if we can look at just the equation and determine it. Look at example 3. First of all, is it a polynomial? In example 3, page 159 at the bottom.
Yes.
Is it in standard form?
Yes.
Then the leading term is what? Anyone?
0, 1, 5, 1, 2, 8, 0.
What? Example 3?
For you.
It's negative 0.5 x. Wait.
The leading term is negative 0.5 x to the fourth. All of that is the leading term. Is the leading coefficient positive or negative?
Negative.
And is the degree odd or even?
Even.
Which one of these up here are we looking at?
We're looking at the negative, so the second one.
The second one, which means starts low, ends low. And you would describe the end behavior this way. You following? If it were not in standard form, you would hunt through and find the highest power, because that would be your leading term, and you'd make your decisions based on that, even if it doesn't lead. We okay? All right, moving on. The next thing they want you to do is to graph a polynomial function. This is where you're going to have to learn a skill with this guy and copy it extremely carefully on paper so that you can answer a test question, or you can put together a graph and focus on certain points of it or whatever. But this can do the grunt work for you. But you have to be a good copier. And I don't mean just throw a sketch in. There's got to be certain things that you do, and I'm going to show you how to do that with your calculator. So I'm going to put this over here and aim this towards the grid a little bit, because we're eventually going to copy it on the grid. Put both of these in the same screen. Yep, like that. Okay. So we're looking at the next example on the following page. I think it's example 4, is it? Is that what it is? Okay, and here's our task. Doesn't look very hard when you first write it. It says graph. Graph that function. Is it in standard form? First of all, is it a polynomial? Is it in standard form? How will you expect it to behave? You may use informal language.
Okay. Negative, even. Right.
The A part.
Okay.
It's what? Well, the leading term is, the coefficient is, yep, starts high, ends low. Yep, so we expect it to begin up over here and then end up down here. Okay, so here's what we're going to do. We're going to make the calculator graph it. So turn your calculator on. I got to plug this in. Okay, so we're going to go to y equals and clear out anything that's in there. Make sure your plots are off. They shouldn't be on. We haven't done that for a while. And then we're actually going to type that in there. The author wants you to take some values of x and plug them in and pull out some values of y's by doing the arithmetic. We're not doing that. Calculator can do it all for us. Get those values anyway. So it's going to be negative x raised to the third plus x squared plus 3x minus 3. Since this has no context, no story problem to it, we're just going to start with the standard screen and see if we can see enough. So we go to zoom standard. Okay. Did it do what we expected?
Yeah.
Yep. Started high, ends low. How are you going to copy that thing exactly? Well, we need some points to plot. Yes.
So if you find your minimum and then your maximum of the curves.
That's going to become very important. That's very good, and that's good instincts. And we will do that in just a minute. I want to show you some way to at least get some points on here that you can actually plot so that you can connect them carefully and get an accurate graph. Are you with me? And minimums and maximums are going to be very important. So there is a way to generate a table like they have in example 4. Are you looking at example 4 with me? See that table they've got there that has the little tan boxes? They've got -2, -1, 0, 1, 2. There's a way to get your calculator to generate that without having to plug in each of those x's separately and kick out a y value and maybe make a mistake. And it's called a table. See the word table set above the window key? Right here. Right here above the window key it says TBLSET, table set. That's where I'm going. So we go blue, table set, and this is what it looks like. And this is what it's talking about. Instead of saying, this is the first question it's asking you here is, what x would you like to start this at? It's saying table start because it's not always x. This thing's capable of graphing in 4 different ways, and the always x. So they don't say x start. They say, where would you like to start the table? What independent variable would you like to start on? That means x to us. This right here says, how would you like to increment those x's? Now, if you've got a problem that you're doing where you're talking about what happens from one century to the next, then you probably want to number your x-axis by hundreds. But this thing has no context. And it looks to me like the graph that we made on a nice standard screen is going to, we want just incremental x's, one at a time. So this is a good choice. Now, right here, where do we would like to start the x? I do not want to start it out here at, say, -7 or something. The reason I don't is because the y value that's going to go with it, if you think about the way this thing's behaving, if I come out here, I am going to have to go way the heck up outside the building here to get to a y value that goes with this number. So I don't want to start there. I want to be able to plot some points somewhere near the origins when I use up too much graph paper or have to count too far. So it looks to me like -3 is about as far left as I want to go. And even then, that's up there a ways, right? Are you with me? So this graph can determine where you would like to start your x's on the left. So I'm going to go back to my table set, and I'm going to choose -3. And I'm going to go -3, then -2, -1. That's what this is telling you. It's kind of like the scale on your graph. Then, do you see the blue words, the word table above the graph key right here? See how it says blue and it says table? So you hit second function in the graph key and it will give you a table starting at -3. But choosing -3 is still not a point I want to plot because I don't want to count 24 and I don't want to waste that much graph paper. So I'm going to ignore that one. I'm going to start here. And I'm going to start plotting these points that the calculator generated for me on my piece of paper where I have to report my answer. So I'm going to grab my calculator, look at it. I've got the point -3, 24, which I don't want to plot. Remember, here's the origin. I got a -2, 3. That's a point. I've got a -1, -4. This is how you graph accurately, folks. It takes a little time, but at least you don't have to do the calculating. The calculator did it for you. 0, -3, 1, 0, 2, -1, and 3, -12. I might count that one. There's 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. If I get y values that are in the early teens, like 12, usually I'll count those out. And you look at what you've got there, you go, crap, I don't have to do that. Well, go back to your graph and look at what the shape is. Can you see how you're going to be able to pick up those points? But the thing is, you're going to have to make it bottom out and top out where it belongs, which is where your idea comes in. So when you get back to the graph, there are 2 more points we got to plot on this graph, and that is the bottom little hook thing there and the top. I'm talking about this. We need to find out this point and this point. Now, you could ask your calculator for maxes and mins, which would be great. I'll do that with one of them. So I'm going to calculate minimum. That's my left one right here. I want to calculate that. So I've got to get to the left of it and hit enter. Then get to the right of it and hit enter, and don't guess. And I get -0.7 and -4.3. So I'm going to go -0.7 and -4.3. 1, 2, 3, 4.3 is about right there. So that tells me where I'm going to bottom out. Now let me show you a quicker way to find out, because you can't possibly graph better than 1/10 of accuracy here. So rather than actually find the 0, which takes a few extra keystrokes, instead just hit and move it until it appears to be right at the peak. That appears to be a peak to me. Maybe one more over. Maybe not. Anyway, one of those is going to work. Where is it located? It tells you right down here at about 1.5 and 0.3. So I didn't have to find the maximum. I just traced it. What did I say? 1.5, 1.5, and up a smidgen, just above the x-axis, about right here. That's where it's going to top out. This is how you make an accurate graph. It wouldn't hurt at times to find these zeros, although they won't help us much here because there's not much up above there. Sometimes you can find the zeros so that you make sure you hit the x-axis in the proper place too. Those are things you might want to find to improve your accuracy. Anyway, this is how it's going to go. We look at the shape of that graph and we try to make it all work out. This thing's going to turn, and by the way, polynomials never have corners. Never. They may turn really sharply, but their turns are always roundy. So try not to make corners when you're graphing these. Go like that, come up here, and it's going to top out right there. Turn, and go down and try to grab this one. That would be fine. That would get you 100% on this one. So you can plot just individual points by going to the table. You needed to find your maxes and mins by either tracing or actually asking the calculator what they are and get those plotted too, so that you bottom out and top out where it belongs, not just somewhere between this point and this one. Actually does top out where it goes. Do you understand how to do that? Just you follow that? Okay. So your graphs must be copied very accurately. Since this guy's doing all the calculating, you better be a good copier. Okay? Okay. This next part is where people have the roughest time. Try to follow my thinking, because this is not something you can just brokely learn how to do. You're going to have to sharpen up your thoughts a little bit here. On example 5, I would like you to cover up the solution. Do not look at it. So on example 5, I want you to cover up the solution. What happens with things like example 5? They are going to give you bullet points of things that must be true, and you've got to create a graph that has all of these things true. Let me read to you the bullet points, and then I'll teach you how to wade through them properly. We are to sketch the graph of a polynomial having these characteristics. F is increasing. By the way, do you remember what increasing means? Did we ever discuss that? Oh, dang, I wish I hadn't. Pretend that I hadn't erased that graph and it just went like this. Just pretend that was it with me for a second. This graph right here, let's see, the origin is right here, and this thing appears to bottom out at about 0.7 and top out at about 1.5. That's pretty close to what we had before, negative 0.7, okay? What we're talking about with increasing and decreasing the way you tell, or the way you report it or answer it is x values. X values that do something, where the graph does something in that range of x values. This graph is decreasing. You always pretend that you always move right. You pretend you're a little bug on the graph. You're stuck to the graph. You cannot get off of this orange thing. So if you're here and you want to move right, you're going to have to go down. That means you're decreasing in all of this range. But it's not the y's we're talking about. It's what the y values are doing over this range of x's. No matter where you are in this graph, because it goes up like this forever, if you're out here and way the heck up there on the graph and wanting to move right, you're going to have to come down. So this thing decreases all the way to negative 0.7. And this is the way we write it. It decreases on the interval from negative infinity to negative 0.7. Or for x's which are less than 0.7, negative 0.7. That's where it's decreasing. It's also decreasing from 1.5 on. So it's not only decreasing here, it's decreasing here. Not and, it's or. You following me? But it is increasing between those two. It's increasing because when you, from negative 0.7 to 0.5, x values right here, if you're on this as a little bug, if you want to go right, you're going to have to go up. Do you understand this concept? Now that you understand that, here goes this tough problem. Let's read these words. Don't look at the solution. It says, f must be increasing to the left of 0 and to the right of 4. What I just said is called math fluency. When you started learning to read, you were busy trying to sound out words with phonics that you learned, but by the time you were done reading it, you spent all of your effort and mental capacity trying to sound out words, and when you got done, you had no idea what you read, because you were busy sounding out words. The meaning was lost, right? You were not fluent at reading at that point. When you are fluent at math, you do not read what is written, you read what it means. So most people that are not fluent with math would say f is increasing when x is less than 0 and when x is greater than 4. When you're fluent in math, you read that by saying f is increasing when x is to the left of 0 and to the right of 4. Why left and right? Because they're talking about x's. So you put some boundaries on here, and it doesn't hurt to have some colored pencils here. There's a marker at 0 and one at 4. And what it tells us is that graph is increasing left of this. So it has this general gist to it, increasing up to the right, right? And to the left of 0, but also to the right of 4. That's a general idea of what this graph's going to do. Next bullet point says f is decreasing between 0 and 4. It's starting to take on a shape that I think I know what's going to happen here. I've got some more specifics to pay attention to, though. Do you understand what I did so far? Now, we talk about positive and negative values. Positive values are above the x-axis. Negative values are below. I mean, y values here that are positive or negative at certain x's. So, the next bullet point says f of x is positive. That's how you read that. The y values are positive between -2 and 3. I'm going to put the -2 and the 3. I'm going to put those on there with a different mark than I did here, maybe even a different color. And between these two values, the graph has to be above the x-axis. So it's got to go like this. Somewhere or another, it's got to go like this. But remember what we had before, right here, it has to stop going up and start coming down. That's where it breaks from increasing to decreasing. And sure enough, look what I did. Right there above it, right there, I stopped going up and began coming down, but I stayed positive the whole way between these two. That's what the third bullet point's saying. You following me at all? This is rough. This can be tough. It takes an awful lot of concentration. Keep track of a lot of things in your mind at once. It is also positive after the number 5. That's how you read that. When x is bigger than 5 or after 5. So I got to count that out. Here's the origin. 1, 2, 3, 4, 5. So here's another x. And after that, it's going to go, it'll be positive right here. And this indicates it's going to be increasing. So I got that much of it. How we doing? You understand what's going on, kind of? Then the last bullet point says f is negative. In other words, we're below the x-axis. For things left of -2, here was -2. And it follows this track there. That's good. Left of -2. And it's also negative between 3 and 5. This was the 3. This was the 5. And we have to stop decreasing at this orange point. We have to stop decreasing and start increasing there. The only thing that's not stipulated in these words is how high we go here and how low we go here. That I would not grade you on. But it's got to quit going down and start going up when it hits this orange point. And it's got to quit going up and start coming down at this orange point. And we've got to have positives between here and here and negatives between here and here. All those bullet points have to come together. And if you now uncover the solution, you'll see that's just what they got. It would be wise of you to erase these indicators. He didn't. He left those on just so that he could make the point. The author did. But it would be good of you to erase those because they aren't really part of the graph. This is what you should have. And if you leave your x's and other points there, that's okay. That's a tough problem. That's a tough thing to do, especially if they have 6 bullet points instead of 4. Then you got some trouble. You'll see. I think they're only going to do ones with 4. Last thing. Example 6. You may want to get back on this video and refer to the making of this so you can kind of get an idea. Stop it and start it as you're trying to put one of these together. It'd be tough. Okay. Do you think there'll be a problem like that on the test? Yep. Better get good at it. All right. Example 6. This is now a story problem with context, which means we got to do a little harder thinking about the sizes of our windows. We're still going to let the grapher do it. Here's our scenario. We have electric vehicles that are sold in the United States. That's what we're talking about. The estimated number V, that's what it is, in thousands of electric vehicles in the United States can be modeled by this polynomial. It's a cubic polynomial. Is it going to start high and end low or start low and end high? Start low, end high? Because it's got a what? How do you determine that? Positive leading coefficient. Okay. So what we're going to do is we're going to put that in our calculator in just a minute, but let's see what they're after here. It says where t, that's our variable, like x usually sits there, but it's t this time, represents the year with t equals 1 corresponding to 2001. So if t equals 1 goes with 2001, when did this study start? It's not that hard a question. Let me ask it again. Look at the words and see if you can focus on what I'm asking. If t equals 1, when t is the number 1 corresponding to the year 2001, then when did we start this study? Yeah, in 2000, when t was 0. That's when we start things, when time is 0. But this goes from the first year, after the first year is elapsed, up to the 10th year, which you'll see in just a minute. It says use a graphing calculator to graph the function for t between 1 and 10. What they've told you, folks, is your window for the x's, because that's what t is the x's. So we're not going to go from negative 10 to 10. We're going to go from 1 to 10. That's what they just told you in that first line of A. Where t is between 1 and 10. They have given you the x min and x max. You've got to be able to interpret it that way. Describe the behavior of the graph on this interval. Does anybody have any idea in thousands how many electric vehicles there were in the early part of this millennium in the United States? No, nobody knows that. So when you go to design your Ys, you're going, well, geez, I don't know what I want to do with that. So we don't have any inkling for the Ys. Let me show you another aspect of your calculator that's pretty cool. So what I want you to do first is go to y equals, and I need you to put that horrendous cubic function in there. That's ugly thing. And we've got our x's designed. We left y's at negative 10 to 10. When you get done, graph it and see what you can see. Nothing. This tells you it's working on it because it was a nasty one, but it's done graphing and you're going, crap, now what? Here's what. If you know your x values and you've set them, a way to find where this graph shows up on the y values by going zoom and going clear down to the 10th thing. It says zoom fit. It will keep your x's, but it will adjust itself until it can show you something that are y's. It'll show you something, and it'll usually do it pretty well to fill up the screen. What's that? That doesn't quite look like the graph that, well, it's pretty close. The graph that they have on in the solution to the problem, but it's enough. We can see everything going on between 1 and 10, even though most of it's occurring up here, we can still see it all. So when you're trying to figure out the y's and you don't know what they ought to be, but you do know what the x's are, you're pretty sure, go zoom fit, and it will show you something. Then you can adjust your y's from there if you like. So it says, use the graphing calculator to graph the function from 1 to 10, which we did. Describe the behavior of the graph on this interval. You're going, well, I don't know how to describe that. Here's how you describe it. At t equals 1, it is increasing until it gets to about 1, 2, 3, 4, 5, about 2005. Then it appears to go to stay the same until about 2008, and then it appears to start increasing again. That's how you describe it. Okay? Talk about increasing and decreasing. At certain x values, it switches gears and does something new. Okay? Then it says in B part, what was the average rate of change in the number of electric vehicles in use from 2001 to 2010? In other words, folks, and we've run into this phrase before, we haven't seen it a lot. It means to find the slope of the line from this point to this. That's the average rate of change, it's the slope of that line. What do you need to find the slope if you're trying to find the slope between the beginning and the end? What do we have to find? 2 points. This point. And this point. How do we find points on the calculator? Particular points. Could use the table, although that's not the most efficient. You ask it from the graphing thing, what's the value when t is 1? So you go second calc a value when t is 1. The value is 18.58. This is our beginning point. First year, 2001, 18.58 thousand electric vehicles were running on the road by then. How do we find out what it is at 10? Ask it. What's the value when t is 10? And the answer is 58.57. It's those 2 points we have to find the slope in between. Remember how to calculate a slope. It's Algebra 1 skills. Not x. Y's. And remember, slope is rise, which is a y thing, over run, which is an x thing. It's got to be y's first. So it's going to be 58.57 minus 18.58 over, same order, 10 minus 1. Just for the sake of brevity here, pretend this is 5/8. It's so dang close. So what's 58? Hang on. What's 58.58 minus 18.58? 40 over 9. How many times does 9 go into 40? About 4 and a little bit, about 4.5.
Yeah.
So the slope is about 4,500 vehicles per year were bought. We'll continue this tomorrow, but you have plenty to get that assignment started. So you get as much done as you possibly can. We've only got one more question to answer. If you're doing it in writing because you didn't get a good enough score, or just because that's what you want to do, here's the assignment. 1 through 21 odd. 22 and 23 to 43 odd. In other words, 1 to 43 odd and include 22 somewhere along the line. Okay? Lab's open till 7 if you want to come get started. Good luck. That's it, guys. See ya.
Can I come to the chapter 4 test on Monday?